So, hi, I'm Michael Landy. Welcome to the second week of our mechanical engineering research seminar. And so this week we have Dr. Pierre Larochelle, who many of you might know as professor and department head of mechanical engineering. And he'll talk today about some of his research about kinematics and robotics, and in a particular context of additive manufacturing. So take it away. Thank you.
Thank you, Mike. Thank you for this opportunity. As I put the talk together, I was thinking, I'm here 3 years, and this is my first time giving a technical talk. So I'm glad it's happening. Also, another thing that's unique about this talk, for me anyway, is that, I've given talks for a long time, but I believe this is the third talk I've ever given that doesn't have an equation in it. There's not one equation in this talk, so it's very conceptual, and well, hopefully you'll find it informative, and you'll remember this the next time I give a technical talk, because it'll probably be full of kinematics equations. So I'm going to talk about some work I did with my most recent PhD graduate, Ismail Usri, and we're going to talk about his efforts and his contributions in trying to utilize industrial robots for preformed spatial additive manufacturing. Ismail came to me with a background in manufacturing engineering and mechanical engineering, and he knew he wanted to do something in additive manufacturing. And through many months of conversations, we ended up working in this area together. So here's an outline for the talk. I'll give you an introduction, a little bit of a motivation as to why the heck are we looking at this, and what interests us. We'll talk about the platform we put together, robot arm-based platform for FDM fused deposition modeling. We'll talk about our 3D lattice structure generator that we created. We'll show you some experimental results, a couple of videos, and some things that Isma and I are continuing to work on. And of course, we'll acknowledge some folks. So for the introduction. So my background is kinematics. I'm interested in motion and complex, interesting motions. And conventional 3D printing, as you see here with all these traditional off-the-shelf 3D printers, quite frankly, bother me and bother Isma, because they call them 3D printers, and that connotes to most people the ability to print freely in space, because we think of space as being three-dimensional. Well, space isn't. The space we live in is six-dimensional. And these 3D printers are really, from a kinematics perspective, 2.5D at best, 2.5 dimensions of printing. And so we were looking and wanted to look at, well, how can we do true preformed spatial manufacturing using FDM, fused deposition modeling. And in fused deposition modeling, of course, you're melting plastics and fusing them to build up parts.
Let me click on that.
All right, so click on that. So on the left, you see what happens in conventional 3D printing. Or say you wanted to print, these letters, like you would slice them horizontally, and then you would print them out on a build plate.
So I'm sorry that's not working. Let me see if I could. That's right. Technical difficulties. Correct.
Hold on.
Do you know any good kinematics jokes?
So
There we go. almost
Okay.
go. There it goes.
We got mine.
All right, well, if that one works, and hopefully the other ones will work too.
Maybe not.
Don't worry about playing it again. Just go back one. I'll just go back one slide and come back to it. So a kinematician walks into a bar. I don't have to joke this all well, hang on. Well, Mike is working on this. So anyway, it's just a short video. I'm more concerned about the videos later on. It's just a short video to show how traditional, what we call 3D printing is done, where whatever it is that you want to print, you slice it in parallel planes with software literally usually called a slicer. And then you're adding a little bit of material, and then you go to the next layer, add some more material, and eventually you build up a part in one direction, right? In the vertical direction in this picture on the left. And the little video on the right is just a video showing that the additive manufacturing process that's done with conventional 3D printing. Keep going?
Yes.
All right, okay. So from a kinematics perspective and also from an additive manufacturing perspective, that's very limited, right? When you can only do 2.5D printing and you've got to print in these parallel planes. So what we wanted to look at was, well, can we use something that both of us were very familiar with, which is traditional industrial robot arms that have 6 degrees of freedom and can arbitrarily position something in the 6-dimensional world we live in. So could we use an industrial robot arm to do true 3D FDM additive manufacturing? So that was one of the objectives of our work in collaborations. And then we wanted to get to the point where we could actually generate 3D lattice structures. True 3D lattice structures printed in free-form space. I'm not clicking.
No, I am.
You're clicking? Okay.
Yeah, right. And
Well,
so,
maybe the clicker was going back.
yeah, sorry.
That's okay.
You see a window on the video. We don't see a window. So. Okay, I think we're good.
Okay. So these are the two objectives that we're looking after, right? Okay. Could we use an industrial arm for true 3D FDM additive manufacturing? And could we generate an algorithm that will enable us, if we have such a platform, to actually generate 3D lattice structures in 6-dimensional space? And so this picture here is just showing you like what's being done today with conventional 3D printing when people are making lattice structures. Is you have some lattice structure like we here, which is a simple cube-based lattice structure, right? And in traditional 3D additive manufacturing, every one of these threads that you want to print, even if it's in the vertical direction, which is the direction you're building the part in, you're going to slice that thing. And you're just going to make it into little slices. You know, you're going to make this strut by doing a print of one layer, then another layer, and then you finally get the part. Where what we wanted to be is generate this kind of a system so that we can generate a true 3D lattice structure and actually, well, we want to make this strut, not slice it up like this, but just extrude in this direction and make that part with one extrusion process. And that has lots of advantages in terms of print time, as well as the resulting material properties of the object once it's done. Because your strut is going to be a lot stronger in all directions because you're going to have one continuous extrusion here rather than a bunch of fused layers, which are very, very weak in shear, which is what's one of the negative drawbacks of traditional 3D printing, which is happening now. So those were our two big. There we go. So there were other people trying to think and work on this topic at the same time, right? So here's a couple of them that we'll talk about. Keating and Oxman developed this system, and I'll zoom in that picture for you here, using a Cartesian robot, So it has much simpler kinematics. So a Cartesian robot just has pure translations in X, Y, and Z and doesn't do any rotations. And then they put an FDM, a fused deposition printhead, on the end of that 3D Cartesian robot. One version of a Cartesian robot is a gantry robot. So if a Cartesian robot throws you off, you understand what a gantry robot looks like, or even just a gantry crane in a warehouse, same kind of thing. And so here's the printhead on the end of there. And by using the gantry robot and then moving this printhead in X, Y, and Z directions, they can print out a curved structure and a cubic structure like this, and not necessarily print in parallel slices to what we call the build plate or the build plane at the bottom of the plate. So they were able to make some nice contributions there. I'll also talk about Li Wei and Chung's work, and they developed a system to try and do more than 2.5D printing using a 5-axis CNC machine tool. So kinematically, you see a kinematic diagram here of a CNC machine tool. I'll show you a blow-up of that picture. And so basically what you think of is in real simple terms, and the crude way to think about it, take a 5-axis CNC machine tool, which is a mill, for example, and take away the mill head and the spindle and take that out and replace it with a 3D printhead. And that's what's done right here. So the spindle was here, all that was removed. All that was added was the FDM printhead here. And so you've got the positioning of the CNC machine tool, which is very, very precise and repeatable because it's a very nice, stiff kinematic structure. What you don't have, of course, is you don't have any rotations. Okay? So you're able to do printing along the 3 Cartesian axes, but you're not able to rotate anything in the CNC machine tool, 5-axis CNC machine tool. So then we wanted to explore, okay, well, let's use a traditional industrial robot arm and see what we can do and what we can get going, and see if we can come up with an FDM platform. And so here's kind of like a system diagram of our Motor Maker platform. We call them Motor Maker because we have a Yaskawa Motor Man robot, and we were going to try and make stuff with it. So we call it Motor Maker. So on the left here, you see the Motor Man SV3 robot. It's not a big robot, but it doesn't have to be a big robot. It's got an arm reach of about 1.6 meters. It's rated for a 3-kilo payload. That's the 3 at the end of the name. And that was controlled by a Yasnak XRC controller. So you see the controller there on the right. And so what we did is we took that industrial robot, and instead of doing traditional end-of-arm tooling on an industrial robot, looks like it was done with the 5-axis CNC machine, taking off the spindle and replacing it with a printhead. So we put a printhead at the end of the robot, right at the hand. So here's the head with the heater. We of course, we have to feed our plastics to it, so we have an extruder feed motor. We've got a controller board, which is controlling the heater, a couple other things which we'll talk about some more, as well as the extruder feed motor. And that controller got to talk to the extruder head, the cooling fan, feed motor, and it's going to talk to a PC, and that PC is going to talk to the Yasnak XRC robot controller, and it's going to do that using Motocom SDK, Software Development Toolkit. Motocom is a proprietary communication protocol provided by Yaskawa Motorman, so that you can talk to the robot controller while it's actually controlling the robot and running the job. And so it's kind of a high-level system overview of the concept for the Motor Maker platform. And here's kind of a line diagram focused on everything that's involved in the FDM process. So here you see the robot. Right? So here's the robot arm in the schematic here. You see the filament, right, for the 3D print here. You see the filament being fed. And the feed motor. And you got the print head. And you've got the heating element, right? This other line here, different colors in the filament, that's compressed air, which comes into the robot. And just schematically, we're just showing up compressed air coming in here. And then we have a nozzle for the compressed air here out of the printhead. Because when we're going to, we anticipated this and we were right. If you're going to do freeform 3D FDM, what happens is, of course, when you're printing in any which direction, you need that plastic to cool off and solidify so that it doesn't creep, right? And so we need to cool it off quickly. And so our controller board is also controlling the flow of compressed air through this nozzle, which is literally just blowing on the plastic once it's been extruded to cool it off, so it doesn't creep on us. And then here's the extruder driver board. And what we used for the external controls, we used an Arduino Mega, which is talking to the PC and talking to the industrial robot controller. So what did all that look like in hardware? So here's a picture of the hardware system. So the filament spool is inside this little box. We made this box because we had to make this box. We did some experiments and things weren't working well. And what we found was that the temperature variation and where this work was done is Florida, and the humidity variation were causing lots of issues, and not just with what we were doing, but with all kinds of 3D printing going on inside our facility. So this box helped us to control the airflow around the filament spool. So it's just literally a box that keeps the airflow slowed down. So we got the filament coming out here. And of course, we mounted all this on the robot arm. The extruder controller here, the Arduino Mega, is out here mounted on the elbow of the robot arm. Then we've got the electronics and the compressed air coming out here, right? The extruder's right here. And then the printed part, and then the build platform is just a large plate built on next to the robot. The printed part here, if there are any mechanics people in the house or online, looks like a dog bone that you would make and use for material testing in an MTS machine, and that's literally what we were doing here, is we were making dog bones for testing in the MTS machine. Because we were printing and making those dog bones by extruding material in any which direction. And we wanted to compare and contrast the material properties of these printed parts using our MoldMaker processes versus a traditional 2.5D printing, and looking at the advantages and resulting material properties. And we got some nice results there. So this picture here was overlaid onto it. The coordinate frame here is showing you the process and the coordinate frame that we've used to plan for all our motion and plan for all our building. So we needed a fixed frame to build with respect to, and so we use that frame, and then do all our motion planning and all our extruding with respect to that. And then down there over here, you see one printed specimen. So here's a close-up of the hardware of the print head. So this is the robot arm out here. The robot arm ends right here. This is the flange of the robot. And so everything is packaged in here, right? Where you've got the compressed air outlet from the robot, which feeds into this tube over here. The extruder feed motor is here, and the cooling fan motor is right here. And that's where the compressed air to cool the extruded plastic is. So we'll talk about a little bit of how we were able to get all this thing working together. So we'll start out tool paths. So the tool paths, if you're familiar with CNC G code, there's G code right there for you. Right? So what our software produced was G code, which we then transferred over into the Escala Motorman XRC controller to translate into robot joint motions in order to accomplish those and realize those. So the G code comes into an interface program. The interface program through the internet with a wired internet connection through the Ethernet goes into the XRC controller on the robot's controller, and the robot controller with that fixed coordinate frame that we just talked about, and the motion speeds that we calibrate the extrusion process toward to, and then we make the robot arm move and do what we need to do. And there's the interface program also on the PC talking to the Arduino Mega through a USB serial. And that's planning all the process parameters, things like fan speed, extruder temperature, the speed of the extruder motor, which controls this extruder motor, the extruder head, and the cooling fan, these process parameters for 3D printing. So after a lot of experimenting, what we ended up identifying is key process parameters for printed parts was our motor maker system, were layer thickness, how thick are we going to make the layers, deposition speed, how fast are we going to be depositing material, and the flow rate through the extruder and the nozzle. And then for our process planning parameters, very important for us with the Motormaker platform was orientation. How do we want to, and what orientation do we want the printhead to be when we want to extrude material? Not even a question when you're using a traditional 3D printer, it's really a 2.5D printer. Right? The orientation of the nozzle is always going to be the same. It's going to be vertical. And you're just moving it around in X, Y, Z, and then you don't have any choices. So the good about employing an industrial robot for this is that, well, now we have all this freedom. We've got 6 degrees of freedom to put that nozzle anywhere we want in space and then orient that nozzle anywhere you want. So with all that capability, then comes the next question. Well, what's the best orientation to put my nozzle in so I get the best result in the part? So this was a big question that we spent a lot of time investigating. Support structure. When we started out, was like, well, are we going to need support structures? Are we going to have, which is done in typical 3D printing, right? In 3D printing, if you want to have something with a cavity in it, you want to print above it, then you're going to need a support structure for when you put that material. And then later on, you remove that support structure, and then you've got a hollow cavity or an overhang or something like that. Well, our hope was that with the Motormaker platform, we would be able to free-form additive manufacture and not use any support structures. We were hoping that we'd be able to do that, especially with the cooling fan that we had at the end of the robot. And then how do you slice the parts? How do you decide where you're going to extrude material? And again, in traditional 3D printing, right? You're slicing, and the only parameter you really have to worry about is how thick are your slices. And then you're just going to slice. And then you have to identify, well, does material need to go there or not? It's kind of binary. Right? Well, when you've got a 3D solid, which direction do you want to slice in? Right? If I'm going to build up a lot of material, which directions do I want to be depositing material with my robot? And then once you've got that figured out, then of course I need to plan the tool paths, for my robot arm to do what it needs to do to put the printhead in the right place. Well, those are some of the big process and planning parameters that we identified. So, yeah, I guess the little menu bar for Zoom is blocking out the caption at the top there. But these are factors that, you can probably put, thanks, Michael. Factors that we identified as being important in both looking at the literature and our experience with traditional 3D printing, that we thought would be important in terms of mechanical properties of the resulting 3D parts with our Motormaker system. Things like the perimeter, how many layers, what thickness do we want to have on the perimeter of the part? If the part's a solid, you don't print and extrude plastic throughout the whole solid, right? You put walls, the perimeter, and you have some kind of rastering and scaffolding that happens inside the interior of the part. And then, what's the layer height, right? And what's that raster angle, right? You can see here inside, the support, right? Because it's not solid print. And then, of course, other things like orientation of the print. Do I want to make this part so it's lying horizontal? Do I want to make this part so it's in the vertical or some other orientation? And of course, print speed, temperature, raster width, and the air gap sizes. You see the gaps in here. And what's called infill density, which is what I'm talking about, the ratio of material to the volume. So it's happening inside the solid part. So I'll talk a little bit now about the 3D lattice structure generator that we developed. And so we came up with this algorithm and then, all the equations and all the math and all the stuff that's underneath it. Right? And the idea here is how are we going to take that 3D solid part and how are we going to make it with the Motormaker system? So all that happens in just a few blocks in this flow chart, right? So this is really high level. But somehow we're going to get that geometry, the geometry of the part we're trying to make. And that's going to be the input, right, to the algorithm. So somehow we're getting the information of the geometry that defines the solid. STL file, for example. And then we're gonna take that solid and we're gonna do some region-based segmentation. We're gonna take that solid and we're gonna chop it up into some identifiable geometric regions, which we're gonna make the process simple. So let's take any solid. We're going to identify some geometrically simpler solids within it, and we're going to work with those. So it's just like, like most challenging problems. Right? Take a tough challenging problem, how do you solve it? Break it up into a bunch of little problems, and hopefully those little problems are less challenging. Right? For each of these little segmentations, we're going to figure out the direction to build. Which way do we want to be building the part? Which direction in 3D space? And then we're going to generate a lattice structure to realize that solid, and we're going to do it with multi-axes. So it's not just with one direction, but we're going to build a lattice structure to support that solid in different directions. And then so that these two happen for each region, and then what we have to do is figure out a sequence. So if I take a complex geometry and I break it up into a bunch of little pieces, well, there are probably there's multiple ways that we can make the little subregions to yield the final part, and then we need to ask ourselves, are they all feasible? And so we actually explore the geometry to figure out what sequence do I want to build these individual segmentations in to yield the final part, and not get the robot tangled up as a pretzel, or not have subparts collapse and fall or fail during the build. And then once we got the whole thing planned, and it was chopped up into segments, we figured out how we're going to build each of those, how we're going to fill them up with a lattice. We figure out the sequence that we're going to build those segments. Then we take all that stuff that we planned out, and then we need to generate tool paths, which is the actual motion commands we're going to send to the robot. Then once all that's done, send all that stuff out to the robot, turn the print head on, and make the part. So here's the first solid that we worked with. So we thought this would be a nice one to start with. We got this long solid post here, and then we got this little structure with overhangs and steps above, right? So if you're gonna make this on a traditional 3D printer, you probably make it in a couple of parts and then put it together when you want. Right? You probably make this horizontally, this post, and make this horizontally, and then glue them together when you're done. Right? We wanted to have one solid 3D print, and we want to be able to see if we can make this overhang. So we can just roll this out without chopping it down, and then of course build in directions we want to build to get good results in terms of mechanical properties. So here's the region-based segmentation for that part we just looked at. So this is top view. So this is a top view of that part we just looked at. So we're looking down on the steps above, right? And here is that post underneath, okay? And so we segmented the part into those different solids. So there's rectangular solid coming up for part A. Part D is a rectangular solid that's short and pretty wide. And C, you've got these smaller pieces of rectangular solids. And then the letters define those solids. And the next thing we had to do is determine the set of build directions for these guys. And for this first effort, we wanted to constrain ourselves to the 6 Cartesian directions. So we're either going to build in the plus Z or the minus Z, plus X or minus X, plus Y or minus Y. For this part, that's okay, right? Because if you look at this geometry, you can build this just going in those 6 directions. So we wanted to, after we segmented it, we wanted to determine the build directions for each of those segments. And then of course, the way it was decomposed was taking into account the overhang which is happening so that we can try and make it all in one print. So here's an exploded view showing you the segmentations and the direction to build that the software algorithm identified for each of the segments. Right? So we're going to build, for example, part A straight up we're going to build this piece in the -x direction. So this is going to be printed with a print head here, putting literally this layer and then growing the part that way. This part's going to be that started with that rectangle back there and growing this way, and then growing in the positive y, and then this segment's going to be growing in the x direction. So you can see that the actual printing is going to happen in multiple directions to yield the part. And then, of course, what you see, of course, is that there's no support structures or anything like that. It's just going to be free-form printing in 3 dimensions. All right, so how do we generate the 3D lattice structure? We're going to use, so the input to that algorithm is, of course, the segment involved. So we input the segmented model, and again, STL files were fine for all of them. So the next thing is we're going to slice it layer upon layer along the build direction that our algorithm has identified, with each layer being the length of a predefined strut. So we've already done experiments to identify, lattice structure strut length that our system can print well based on the size of the nozzle and the filament and the ambient conditions and all that. Which, in our case, turned out to be, I think for this experiment, 5 millimeters. So that was a strut length. That's the longest strut we're going to print. So we're slicing 5 millimeter slices. And so we do that for our part, and you see some of those slices off to the right. Next, we generate node points along the outside contour of each of those slices. So now you start seeing these dots, which we call node points. Next, the algorithm generates a grid of nodes that are between the outside contours. So you see these nodes. So the first step gave us the ones at the vertices. Right? Now we've got the in-between ones. Next step, and at the same time, we check if the above layer has an intersecting orthogonal line between the generated nodes on both grids. Because when that geometric condition is satisfied, we go, now we'll just print a strut between those 2 points, right? Or less. So that will generate the first set of struts that we're going to make, and then we're going to generate struts along the build directions connecting all the nodes. And so that's what you see outlined in red now. So that part turns into that lattice structure. Now we need the sequence. We need the sequence planning. So after we've done that for all of our segments, we need the sequence as that. Right? We're going to have all, in this case, five segmentations for our solid part. Well, in what order can we print and make our part by making each of these individual segments? And you can't just randomly go, okay, I'm just going to go 1, 2, 3, 4, 5. Which works for how we label this, but if you go with different permutations of these segments and you try and print them in different order, it's not going to work. You're not going to get a printed part, which is obvious to us looking at this diagram, right? I can't make 3 before I make 1, right? Because 3 will just be hanging in air and there's nothing to support it, right? I can't print in the middle, in midair, right? So it's obvious to us, but when you're creating an algorithm and you're in software, you've got to develop all kinds of geometric conditions that need to be satisfied in order so that we have some fixed support which goes to the ground, right, which is down here. So the algorithm identifies that, okay, well, we've got to build 1 first, and then it goes on and identifies, in this case, well, we're going to do 1 first, then we're going to build 2, and then we're going to build 3, and then we're going to build 4, and then we're going to build 5. And it's not just about, is the material going to have something to adhere to, and it's not going to fall, and the robot's not going to collide with part of the part that's already been made. Right? But it's also, the robot has to print, and the algorithm takes into account the printing of the part so that the print head is accessible to wherever it needs to go subsequently. Because you could easily start making a part, and then the robot can't get the print head where it needs to go in order to print the next segment of the part. So all of this has to be taken into account when you're planning the process. And then we also need to worry about the extruded model transition between build direction. So if I'm doing segment 5, I'm building over there, right? So 5's got a build direction coming out this way, so which means the robot head's going to be over here, and the print head's going to be like this, and coming out in layers going this way. And so when I'm done with 5, my robot print head's going to be pointed like this. Right? And I need to worry about, well, if I had another segment I was going to build, 6 somewhere else, my robot's got to get from here to there and move the print head over there. What do you have to worry about? Is that motion going to be clear? Am I going to be able to move the print head over there? Not only that, but when I move the print head from over here and over there, and I don't want to print anything, I've got to worry about the nozzle. If you've worked with 3D printers, nozzles love to clog. Right? When do they clog? Well, when you stop printing, when there's a pausing, if there's an error and you try and resume, things like that. So we have to work with our extruder motor and the robot arm in conjunction so that we can do transitions from different build directions while we're moving the robot and not have things cool off and get clogged and cause trouble. So after all that's done, right, we've done the 5 segments, we figured out the lattice structure we're going to make, and then we do all the motion planning. Well, here you go. Here's the lattice structure and how we're going to make the part. And this segment right here is just showing you the transition of the robot coming in to get to that direction. Start building the robot. So that's the result of the segmentation and sequence planning algorithm. All right, so experimental results. Okay, so enough algorithm stuff. So let's see if I can talk you through this stuff. So this is not that part, it's a different part. In order to just literally have simpler pictures. So we're doing vertical direction, kind of like the first segment in the previous part we've been talking about. So you see the robot arm print head right there from the Motor Maker platform, and there's a nozzle right up there. And then the next segment was just a simple overhang. So now you can see the robot is now doing a build direction in this direction, as I'm pointing here, and layers are being built and cantilevered, hanging in midair, no support structure, nothing, and we're able to, hopefully you can see it online better than how washed out here, but we've got this cantilevered section here, which is just printed in free-form additive manufacturing. Right? Again, with no support structures or anything, and it doesn't creep, it doesn't droop. The material goes where we want it to, and it stays there. Right? So here's a video which is playing nicely, showing you the process. Now this is sped up, right? This is not real time. All right, so I'll show you the intricacies of the lattice printing, and this is the part we've been talking about, and showing you building the first segment, segment 2, 3, 4, and 5, and then finally the finished part. And so we end up with a lattice structure in which none of the struts in the lattice have been sliced. Each one of these struts is one filament of plastic which has been extruded along the direction of the strut in order to yield this lattice structure, which has tremendous advantage in terms of material properties. You guys in the room here, maybe this is better. So if you look closely, you'll see things that look like hairs. Right? They're little tiny remnants of filament, and that's when we stop printing and move the robot to another spot, right? So you get these little hairs that come out. And so we did a lot of work to minimize that. We actually reversed the extruder and pulled the filament back a little bit and we did those moves. This is about 5 times speed, by the way. And for this, that was just a view, close-up view of the front end. This one's just another video view showing you back up, so you see the whole system. Now, I haven't talked about it yet, but the segmentation sequencing also takes into account the fact that, well, you can't put a whole lot of part mass on one side because then the structure would fall over, literally be statically unstable, right? So we build on one side, and then the sequencer says, okay, build on the other side to balance out the static load so it doesn't fall over. Some ongoing and future works. We're looking at different geometric models, more complex geometric models, and seeing how our sequencing and ladder structure planning and motion planning algorithms can deal with those. We'd like to have branching overhanging structures. We haven't worked on and implemented those yet. And then we'd like to go into connected suspension structures, different types of lattice structures. You see 2 different lattices here, right? Here you see an orthogonal lattice, and here you see an inclined lattice. And we've just started importing geometry which has curved surfaces, which then, of course, we fit lattices to. And we're also looking at variable strut lengths. And just so you can get a feel for these things, you can tell me how I'm doing with the camera here.
Yeah, that's perfect.
Perfect. Okay. So can they see both cubes?
Yep. So you can look on the screen behind you so what they can see.
Okay. Woo. So I want to get real close so you can see the lattice. All right. So this is a 1-inch cube for those of you that aren't in the room and can't see it. Well, you can probably tell by my big fingers. Right, so it's a 1-inch cube lattice, and here's another 1-inch cube lattice. Again, printed with the Motomaker platform. So if you guys in the room want to see these, I'll have them up here. So, conclusion. We tried to present for folks today our Motomaker platform, which is a novel robot platform for additive manufacturing. Summarize for you the algorithm we generated to produce 3D lattice structures for multi-plane fused deposition modeling. The algorithm is able to generate toolpaths for multi-plane printing applications based on an input geometric model, scales and other CAD files. We're able to print parts with overhanging structures using our 60-degree freedom robot arm. And we're able to generate print parts with geometric features of the lattice, and we're able to slice it in single plane layering using conventional 3D printers, which we don't have to do. And try to give you a summary of some of the stuff that's ongoing. We're still working on that. These are some of the publications that have resulted from our work at Eastman. So all these are here. So if anybody's interested, there should be an email. You can have a copy of the talk if you want to have all these DOIs and references. Take a look at these papers. These first ones are about the platform itself, integration of the system, all the end-of-arm tooling, the communications, plan and control. Right? That's these 3 papers. These papers are actually about the implementation and doing those dot bone experiments that we talked about. Study of the material properties of what we're able to do, and compare and contrast things like yield strength and ultimate strength of our 3D printed parts versus traditional 3D printed parts, and you can see the amazing advantage you get when you can print the material in the direction you want in order to get the material properties. Acknowledgements. I have to acknowledge Isma. You've heard about us, and now you get to see him. That's Isma bin Aisha. He's at the University of Malaysia, Pahang, where he's an associate professor now and doing great things in the mechanical engineering department. And we have to acknowledge this fellow Motoman. They were generous in their support of this project, providing us, well, discounted robot system, but providing us the Motocom SDK software toolkit, which was key in order to make this project happen, and they're providing that to us gratis. So we thank them tremendously for their support. And at that point, I would say thank you very much and be happy to entertain any questions if there are any questions.
So Pierre, um, so nice talk and nice work. And compare with the traditional 2D. So do you have some like, estimate like how much speed that you can gain like, in terms of whatever the time or that's the premises of doing this.
Well, time is one factor, right? When we talk to the FDM companies, they're more interested in the quality of the build parts, the material properties of the build parts. If you're just, if you're just making something out of PLA to prototype it, and you're 3D printing it, and you just want to get a feel for the shape, then who cares? But if you're trying to actually make a part which is going to be implemented in a product or a system that's going to go out to a customer, and it has to have a yield strength of blank, and it has to have an ultimate strength of blank, and it has to have a Poisson's ratio within plus or minus, then they start getting very interested. Because right now they're very limited as to what they can do with traditional 2.5D printing. And so, for example, if you're interested in material properties, I already mentioned it, we were very excited about the results that you'll find in here. Our dog bone specimens had yield strengths 2.5 times what's coming out of a traditional 2.5D printer. Just by saying, well, if I'm going to do a tensile test and I want to maximize the tensile strength of this dog bone, well, which directions do you want to put the material in, right? And definitely not, you don't want the dog bone to be sliced like this. And it's nuts, right? But people are doing that. Right? And then, if you make the dog bone like this, right? Now you start pulling it in tension, you're shearing all those print layers. They're all shearing against each other, which is the weakest direction for the part, right? So we're able to extrude in any direction you want. So the big advantage, we think, is going to be being able to plan the printing process to yield the mechanical properties of the part that you want and need. That's where we think the big advantage.
Rachel, this is Shine Roy from Electrical Engineering
Dog
Department.
bone isn't made out of struts though, right? So the examples that you showed were more strut based, where everything was in one direction.
We actually did both.
Okay, so my first inkling when I see this is that the cool part is that it can extrude parts that aren't just straight struts. Have you tried doing like curved struts to connect those parts that would go to the ceiling or to overhang? That seems like it would be way better for material properties.
Yes, but it's harder to test. So we've done those things for fun, but we haven't done rigorous testing on any of those yet.
So I guess like it seems to me, I don't know the material properties of it, but it seems like it would be, if you can connect parts while they're still hot, isn't that better than if you're connecting to a part that's already cooled down? Or is that not true?
It depends. It depends on the geometry and the directions you're worried about.
So I guess what I'm getting at is that you started, like you had part 1, and then you had part 2, 3, 4, 5. And I guess to me it's not immediately obvious why you don't immediately start with part 2 when you get to that spot, because that would make a better, stronger connection out of it.
It could.
Good.
Yeah. We haven't got that far.
Okay. What is the half D? What's the 2.5? What is the half?
What's the half? Well, you got 2, right? That's the XY positioning. And then the half is the Z. Because you can't rotate about Z. So it's 2, from a kinematic perspective, we call that 2.5D motion. You've got 2 degrees in an XY plane, and then only one direction.
So Pierre, can I ask another question?
Yeah, ask another question, but if anyone's online and wants to ask a question, unmute and ask away. We're about out of time, but if you have a pressing question, go ahead.
So,
I'll just ask maybe two questions.
you
This is Shine Roy.
used the other three dimension, you have six, but you have another three. Was it used in your demonstration?
And the ones I showed you today, we're printing in the three directions, X, Y, Z. So this is the first step. Now, what we're doing now is we're printing in arbitrary directions with arbitrary parts. And then we're trying to add on to that curved surfaces for convex and both concave features on parts.
Okay. Any commercial implication, any people
Oh, yeah.
express
There's a
interest?
lo- Yeah, we were early in this, but we're not early now. There's a lot of people working in this area. Everything, from, well, I mean, if you go to a construction site and you see one of the large concrete pump trucks, it's got maybe a 20-meter long arm, which reaches over, and I mean, the companies that make those are now wanting to add degrees of freedom to that pumping boom so that they can print concrete in arbitrary directions. NASA's looking for, it's got open competitions right now for spatial 3D freeform printing of lunar base. That's how they want to make the lunar base. So there's all kinds of stuff. It even goes down to on the micro scale. You read all this stuff about 3D printing of biostructures, right? Well, we realize now that they can't just do 2.5D printing to get the biostructures that they want. If you're going to make real tissue and real artery walls, for example, you've got to go in the other directions as well. So they're looking at systems like this, just on a micro scale.
So let me ask a last question here from Cyan Roy. What is the printing resolution? Is the temperature of the extruder fixed or programmable? And let me add a question to my own. What is the limiting build volume using this process?
So, okay, I'll start with the last one. The limiting build volume is the workspace of the robot arm. So if you need a bigger build volume, you get a bigger robot arm that has longer lengths and things like that. So, and then you just put the system on it, the robot tool form. So that's how you take care of that.
Printing resolution.
Printing resolution is determined by the repeatability of the robot arm and the robot arm controller system, which on this system was plus or minus 2/1000 of an inch. Guaranteed within 6-dimensional space. Most of the workspace is like an order of magnitude smaller than that, but that's what's guaranteed.
And then the temperature of the extruder, is it fixed or programmable?
Yeah, that was one of the process parameters that we found in our experiments to be a key process parameter. So that was controlled in real time. We'd have a temperature set point, and then we have a fan and a heater that controlled. The Arduino Mega board actually controlled those to yield, in conjunction with the cooling from the compressed air, to get the temperature we wanted, both at the nozzle as well as outside the nozzle. So we were looking at temperature coming in by the heater in the extruder, and we were also measuring the temperature right outside the nozzle tip, and then controlling that.
Okay, thank you. So we're out of time. So next week we have Dr. Hadi Fekramandi talking about his research. Thank you for joining us today.
Sure.